Hello, everyone, and thank you for joining NOVONIX's Inside Ultra High Precision webinar, where we'll be showcasing how our team is engineering the world's most advanced battery testing systems. My name is Stephanie Reed, and I'm the Director of Corporate Communications here at NOVONIX. Before we get started, I'd like to cover a few quick housekeeping items. Today's session is being recorded, and we'll share a link to the recording with all registered participants tomorrow. If you have questions during the presentation, please submit them through the Q&A box at the bottom of your screen. We'll wrap up today with a brief Q&A session during which our presenters will address as many questions as time allows. NOVONIX's ultra-high precision coulometry, or UHPC systems, deliver the highest level of precision and accuracy available in battery testing today. Built to outperform traditional testing equipment, UHPC enables deeper analysis, novel diagnostic techniques, and powerful tools for lifetime prediction. During today's webinar, we'll take a closer look at what sets NOVONIX UHPC systems apart. We'll walk through key definitions and design elements behind the technology, compare its performance to other systems on the market, and show how this level of precision supports every stage of battery development. Our presenters today are Dr. Stephen Glazier, Director of Cell Technology, and Mike Buck, Manager of Electrical Engineering. Stephen leads the technical development of NOVONIX UHPC, along with our cell prototyping and testing programs, supporting both internal materials development and customer initiatives across the battery ecosystem. He completed his master's and PhD at Dalhousie University under Dr. Jeff Dont, NOVONIX's scientific advisor, where he focused on high precision metrology, cathode material synthesis, and electrolyte development. Mike oversees the development of NOVONIX's PCB hardware and electrical systems, managing design, production, and calibration of our advanced battery testing technologies. He holds a Bachelor of Science in Electrical Engineering from the University of New Brunswick and is a certified professional engineer. With that, I'll hand things over to Stephen and Mike to begin today's presentation.
All right, thanks, Stephanie. Okay, so first I'll go over a brief introduction of NOVONIX and then UHPC, and then discuss why using ultra-high precision test equipment really matters. I'll pass it over to Mike, who will go through what really makes a good cycler, and then how we make ours the best, including some comparisons to other competitive systems out there that also claim to be ultra-high precision. I'll then take it back and go over to some case studies, how we can actually use ultra-high precision coulometry to advance battery technology and make decisions confidently and faster. So NOVONIX Group consists of 3 different arms covering the entire battery space. Our NOVONIX Anode Materials division in Chattanooga, Tennessee, is scaling up and mass manufacturing synthetic graphite anode materials for the battery space in North America. Our Cathode Materials group here in Nova Scotia in Canada is commercializing our patented all-dry zero-waste cathode synthesis technology. And then the Battery Technology Solutions division develops our UHPC cell testing equipment and sells this all around the world. And we also offer R&D services with our in-house prototyping cell line, and we help customers all over the world with their R&D programs, making cells, testing them, and consulting on the results. So not only do we make UHPC high precision cell testing equipment, but we're also one of the world's biggest users of it, advancing our own technologies, our materials, helping our customers around the world using this equipment. So now I'll get into talking about UHPC, and I really want to cover a few things in the name of UHPC. So it's not all about precision. We offer the highest current voltage accuracy and precision for electrochemical cell testing. And I think it's really important to cover off the differences between accuracy and precision, and then start discussing through this whole webinar that we really provide all of that and that both of these are very important. Of course, UHPC just rolls off the tongue better than adding another letter into that acronym. So accuracy is how close to a value, how close to a target or ideal value you can get. Whereas precision is how repeatably you can measure or achieve that value. And then often thrown into spec sheets is the word resolution, which is the smallest detectable change in a measurement that you can actually differentiate between. So just some diagrams down here to help kind of guide navigating some of these terms and what they might really mean for battery testing. So high precision and high accuracy means that you're always measuring the exact target value every time, and you're doing this repeatedly. So this is really important for trying to understand the rates of reactions that are happening, make really confident decisions quickly, and also get really clean data. So things like really nice, clean DQDV can come from really good accuracy or good precision, whereas measuring the rates of certain reactions can come from really high accuracy. Of course, you can have systems as well with high precision, but low accuracy, getting relatively clean voltage curves, but maybe not having the best coulombic efficiency measurements. And then there's lots of systems that span some of these other areas with low precision, low accuracy, and low resolution as well, which limits your ability to really differentiate between certain measurements. We'll get into this as we talk about analog to digital conversion and even looking at other cyclers' data. So before I pass it over to Mike, and he goes into this in a lot more technical terms, I'm going to talk a little bit about why different types of cycler systems exist. Why aren't they all just perfect? And this is because there's many balancing factors that go into designing a system, anywhere from the component quality to how these systems are calibrated and how they can continue to be calibrated through life, and especially things like heat management. Heating goes with current squared. So the higher power you have in a cell testing piece of equipment, exponentially more heat is generated, and that leads to complexity in removing that heat and limits measurement quality. So I've drawn this diagram here to kind of illustrate that you can't really have everything. And we really have to balance what we have in our labs and what we use to do research with this in mind. So here in our prototyping and testing facility, we have this kind of balanced lab approach where we have thousands of channels that are, various amounts of power, typically higher power, low cost, and a lower quality of measurement. And these are what we use to just get hundreds or thousands of cycles to do rate testing to understand, within a fraction of a percent or so, what value we achieve. And this is where uncertainty doesn't matter so much because we're for what we're trying to get out of the systems. And then we have fewer channels, a few hundred or so of our own ultra high precision hardware, where we have more moderate power, lower power, higher cost, but really high quality measurements. And just interpreting where labs sit and where different types of equipment sit. I've kind of drawn these example areas of where other systems in the space exist. So we have like formation systems that are used in gigafactories. We're producing millions of cells a day. So these systems need to be higher power and a lot cheaper and scalable. Development and R&D systems kind of span everywhere within this space. Sometimes you need high power and decent measurement quality and don't really care about cost. Other times, cost is the most important. And then really where the gaps exist in the industry are sandwiched up against this measurement quality axis. And so our UHPC systems kind of fill this area of the void up here where we have moderate power, moderate to high cost, but really focusing on having the best measurement quality. And then this system or this area down here, that's just very difficult. Moving to hundreds of amps and trying to get really high measurement quality starts to really push the limits of what's possible. And this is a gap that still exists now. So to talk about really why all this matters, why do we need ultra high precision? I talk a little bit about what we gain out of battery testing data. And I won't go too much into the detail in this webinar. We have a few other webinars on our YouTube page that dive a little more into interpreting electrochemical results. But I'll just kind of get into it here where this test system that really sits outside the circuit of the battery. We can measure the potential of the battery, and we can also measure the electrons moving through the external circuit and use that data, that current data, that capacity that we get out of it to interpret what happens in the cell. And there are so many nuanced electrochemical reactions that happen in a cell that contribute to the number of electrons we can count. The better we can do this, the better we can infer what's going on in a cell and make decisions faster. Again, I don't have time to get into all of this today, but you can find some of that information in our other webinars. But really, this diagram just goes to show how complex a lot of the electrochemical mechanisms that can happen in a cell are, anywhere from electrolyte oxidation, which I'm showing down here, which contributes electrons during charge to this external circuit, and we can count that through our cycler, to self-discharge mechanisms from mechanical shorts within a cell that also add capacity to when we're charging our cell. And then mechanisms that lead to capacity loss, where we don't count as many electrons on the way back when we've lost this capacity. And all of these things, the better we can count electrons, the better we can understand all of these mechanisms and try to decouple these in the data that we're measuring and interpreting. So just to cover a couple things here, there can be capacity loss that we know as capacity fade. This is kind of a cumulative effect, and eventually you can see this on any cycler through the noise. Then there's mechanisms like self-discharge, which we use some terminology called slippage to define. This is non-cumulative, and really, if there's any kind of bias between charge and discharge accuracy in your testing equipment, you may overcount capacity during charge, undercount during discharge. And what that really does is it affects your ratio of charge and discharge capacity, throws off your coulombic efficiency, and limits your ability to use these types of cycle metrics to do lifetime prediction or try to interpret what types of mechanisms are happening in your cell. So when we look at other types of cell testing equipment, we can see some of these precision, accuracy, and resolution definitions kind of come to life, looking at the data that comes out of cyclers. So here we've got a few research grade cyclers that everyone has in their lab that we can really see some cyclers that have really good precision, but poor accuracy, and are not really measuring or hitting the actual current being provided. And we can see when resolution starts to drop in other cyclers, especially cycler 3 here, which we're moving from more like 24 bits down to 12 or 8-bit precision or resolution. And then, of course, in cycler 3, the accuracy is very poor. Moving to the NOVONIX system, and just to prove this isn't just a flat line, we've blown up the axis here. When we translate this to cycle metrics that we use to interpret what's really going on when we're testing a cell, we can see that those raw data immediately translate to the full metrics. So here we've got really kind of clean traces of coulombic efficiency over time, but these identical cells put on this system all have different coulombic efficiency values. So again, good precision, but poor accuracy with these measurements. And this kind of propagates through with the other systems, cyclers as well. Capacity fade. Eventually, again, every cycler you can see this trend emerge where the cell is losing capacity over time. And then this metric that we use and discuss more in other webinars called charge endpoint capacity slippage, which is really affected by the bias between overcounting or undercounting in charge and discharge, can be used to as a proxy to look at certain types of degradation mechanisms like electrolyte oxidation, donating extra electrons, counting excess capacity. We can see in these other systems, they're really not able to track this excess capacity. It really leads to this mismatch in coulombic efficiency. And this is what really limits the ability to do really high confidence short-term measurements on these other systems. And there's another system that we'll talk about that is in some of our validation studies a little later that Mike will get into, where this system is a lot more competitive with ours, and we'll show how we stack up against that in a lot more detail. So with that, I'm going to pass it over to Mike, and he's going to dive way into components and how we engineer our UHPC systems.
Thank you, Stephen. Appreciate it. You can jump to the next slide for me, will you? All right, so I'm going to try to make it a little bit more digestible from the hardware standpoint of what it takes to make a great cycler and try to break it down into a process and a slideshow that explains it for everybody in this webinar particularly. So really what we want to try to understand with what makes a great cycler is the fundamentals. And we have to understand the fundamentals to really understand and grasp what makes a great cycler. So I've tried to make it down into a few digestible points. And if you can see in the slide, voltage measurement is a fundamental of like the potential energy and stored in the cell. This is one of the fundamental measurements that's captured in the UHPC cycler. Current measurement, because that's the fundamental understanding of how the electrons are flowing in and out of the system and out of the cell. Timing, it's a fundamental part of it because it's what is exactly capturing the moment in time that an instance that a measurement is taking place. So accurate timing stamps and measurements is very important for and critical for these kinds of high precision applications. Environmental isolation and control. This is what makes it so that the systems are very stable and that the measurements that we're achieving and getting from these instruments are as we expect, since we're trying to get ppm levels values. It takes a lot of environmental controls to achieve those kinds of accuracies. Flexible control. We really want to have flexible control because in order to manipulate cells and understand what the cells from a chemistry standpoint are doing, we have to have the ability to be able to run different kinds of protocols and different scenarios, exercising them to get these kind of metrics that Stephen was just discussing. Another part is the traceability of these measurements. The fundamental basics need to be proven by trusted methods and consensus in the scientific community. So we need to make sure that we're following what the national guidelines, international standard communities have governed to be acceptable measurement practices. And we've tried our best at NOVONIX to match and try to capture these in our traceability with our calibrations and our methods to build these instruments. Ultimately, at the end of the day, why did these specific design things matter? Is data integrity is really what we're looking for. We want the most important thing to us is ensuring that our customers are getting the best data out of their instruments as possible, and it's trustworthy. We want our customers to be able to believe the data they're getting, and we've done the due diligence on our site to produce the best data possible. We want it to be a safe and reliable cycler. As you're experimenting with new chemistries and new cells, that's an important part of designing these instruments and a critical part of the hardware design. And then ultimately, when it's purchased, we want repeatability and reproducibility, like repeatability with the measurements where you can trust that when you run the tool, it's going to be a measurement that is quality and what you expect. Reproducibility, that you on your site can reproduce what we're able to output in our labs, and it's accordingly. So next slide, please. So I've broken down the signal path because in order to understand good measurements, we have to kind of go to the root of the equation. So in this case, cyclers are measuring cells. So in this diagram, I've outlined a connection map, basically outlining from the cell to the circuit board. So throughout this slideshow, I'm going to be layering it and explaining it in a way that goes from the root up until the more complicated sections, which would be the circuit board and how we analyze the signals. But fundamentally, if we look at this slide here, we have the cell. That's what we're trying to capture the most information from. So it's the fundamental part of the, and we just went over the voltage, current, temperature, the different things we're trying to capture from it. The next thing that's interfacing with it is the cell holder. Now, the cell holder is not to be negated in its importance because this is the first part that's touching the instrument. So we want it to be as non-intrusive as possible, but we want it to be able to connect and get the information. So conductivity and the different connections of this part matter a lot because that ultimately will affect those ppm values that you're trying to capture at the precision level. So if the cell holder isn't designed correctly, then we're not going to be able to interface with it in a way that's capturing the true data. It's going to skew results and have biases. Next is the chamber. We talk about the chamber, that environmental control. Material scientists know that, as temperature fluctuation changes, humidity, different environmental controls, this all plays a part in how materials react. And this can cause voltages and current differences, which may seem minor, but in reality, when you're doing precision measurements, it will play a major part in what you're seeing in your measurements from instrument standpoint. So controlling that as much as possible is very critical. The cabling, once again, not to be neglected, because the cabling is really the bridging that happens between the instrument and the cell holders. And this cabling is what's going to block your EMI, your magnetic field interference. It's going to be important for, to make sure that the junctions and all the connections flow correctly. If there's any impedance changes between the cables, this is going to cause measurement skew, and it's going to have major issues. So making sure that you have the correct cabling and the way twisted pair to avoid crosstalk, inductive shields, inductor chokes, all these are important parts of keeping the cable magnetic interference and the signals strong. Another overlooked area in the build process and design process is connections themselves and the material of the connectors. Obviously, you want, if you have dissimilar metals in the junctions, this usually creates what's called a Seebeck effect. And it's not common that you see in thermocouple, if you understand what a thermocouple, how it measures. Different materials, the dissimilar metals will create voltage discrepancies. And all those voltage discrepancies throughout the junction points, if it's copper to gold to silver to different metals, all those junctions will end up having different voltage drops, and that will skew your readings at the end of the day. So trying to maintain the best conductive materials and those connectors consistent as possible through the signal chain is critical to keeping a high precision measurement system running and operating the way you'd expect. And then the last part that I want to highlight here is the circuit board, and we're going to go into a lot of detail on this, and it's a critical part where we'll be focusing a lot of the webinar on because it's a major part of how you capture these high precision measurements. So next slide, Stephen. So I can't stress enough that the importance of component selection when it comes to designing circuit boards. If we look at the top here, I've broken down another flow chart now that we're into the actual circuit board. So we've now captured all the signal from the cell through the cables and the chambers, and now we're talking about the signal at the actual circuit board level. So a few things that you have to look at is the filter network, the gain stage, the buffer stage, and then the ADC. This is the front end network, which is known as where all the signal is being processed on the hardware level. Typically, how people refer to it is it's the analog circuit of the system. So what makes a really good analog circuit design? A lot of it comes down to component selection. So when we're looking at designing the front end that's going to measure the signal, depending on how we want to capture that signal, in this case, we want an extremely accurate signal, we have to pick the best components possible. And so I've listed here a few of the components that make up fundamental building blocks of a circuit board: capacitors, resistors, op-amps, MOSFETs, and BJTs. These are all used on our boards in different ways and in different functions. But I want to highlight specifically, if we look at capacitors, for instance, I've listed a few different types: electrolytic, ceramic, tantalum film. These are all different types of capacitors. Now, when you're designing something on paper, it comes across as, you select a value and basically it's an ideal format. And we always can calculate things in an ideal way. But when it comes to the real world, you have real world anomalies. And so different components have different advantages and disadvantages. And if you don't select the correct ones, what you might think from a data sheet, what it's actually representing, won't actually represent that in the real world. So for instance, if we think about electrolytic capacitors, these are a cheap, they're usually used in power supply circuits. They serve their purpose, but not really great for high precision applications. Then you have your tantalums, which are a lot more stable, they're reliable, they're very efficient, they're good cost, but they're kind of a sweet spot. Then you have your film capacitors. These are your really excellent stability, low signal loss, really ideal for precision circuits, but they cost a lot. And there's challenges involved with using those, right? When you're looking at capacitors, a few of the things that we look at is how the dielectric absorption is. Like, is the signal being distorted, in the precision application? How does the capacitance hold up over time? Every capacitor has a certain amount of cycles to it. So will it be able to maintain its in different temperature stability regions? These are all things that we look into. Equivalent series resistance. This is like heating effects, and it also has signal degradation effects, as the ESR, depending on, if you're using a ceramic cap or a film cap, this is going to greatly depend on how good the quality signal is coming through. So you can design a filter network, but if you don't select the right components for that filter network, ultimately speaking, on paper, it's going to look great, but in reality, when it gets to the ADC, it's going to be skewing its readings, and it's going to be skewing the voltage that you're getting to the ADC itself. Resistors, for instance, I've listed a few different types here, but it's kind of the same main point in the sense that, the carbon is your more cheap end resistors. These are your lowest cost, easily available, not very well built. The tolerances are quite loose on them, but they're cheap and easily available. Your wire round were more of a precision resistor back in the old days. They were used for precision, but they have inductive effects that are not as ideal. And then nowadays, there's designs from high precision manufacturers like metal film and metal foil. These are your really low TCR. They don't change much with temperature. They're really stable, really good for current source measurements, and extremely stable, reliable measurements to use for using in high precision applications. These are all things you have to look into. I'll touch a little bit on op amps. So a few things that you need to search as op amps is they're something that we use to basically set up the gain stage and the buffer stage, which is primary stage before the signal gets to the analog digital converter. Now, there's a lot of different types and there's thousands to choose from, but main things that you have to look into with these is how is the offset going to affect the measurement? This is like going to tie into like what Stephen was saying about the different slippage factors. If offsets are off or there's biases at those front end circuit level, your data analysis on the cell level is going to be affected. So we want to minimize these noise sources and these offsets as much as possible by selecting high quality components. It also has to have the ability to reject power supply noise. There's a lot of noise that's generated from the grid, and having ability to reject these noise sources is critical. And we want it to be stable in different environments. If it has a high TCR or it's the source of it has a high error source with temperature, this is not going to be desirable because environment changes will have great effects on your data and it will skew your measurements. You won't be pleased with what you see. MOSFETs and BJTs, we have to look into a few different things. There's a lot of switching circuits on these designs, and there's many different applications for these types of components. But a few of the things that we look into is thermal stability, gain, that they're low noise, that they're going to work the way we expect to. There's a lot of cycle time to them, and that they'll hold up, and their power ratings are going to be stable across many different applications. Next slide, Stephen. So now that we understand the front end network going into the analog to digital converter, this is usually the stage where people start to see on the spec sheets around how you're looking at the precision of an instrument. So on a spec sheet, you'll see, there's so many bits of precision, or there's a resolution to the instrument. This is where the ADC comes into play. So in most cases, there's a few different types of ADCs that are on the market, and these converters are listed below. So your three typical types are successive approximation, a sigma delta, and an integrating, and I'll go through the different applications. So with a SAR, the advantage of them is they're a fast converter, and they are able to get pretty much their whole bit length that they're trying to get. So if it's an 18-bit SAR, they're very good at converting all 18 bits of the signal through. They are a high-speed device. There hasn't been a lot of development in this territory as far as like technology improvements over the years. So it's kind of stagnated around that 18-bit mark. The advantage is, they're cheap to access and they're friendly to design with. These are used in a lot of high-speed data acquisition and your lower precision cycling equipment. You'll see these in just because they're easily accessible and readily available. Now, your sigma delta type, this is what we use in our equipment. This is a specifically designed more for higher precision applications, but there's many different nuances that come with this type of architecture. They come in a variety of different resolutions, that from 16-bit all the way up to 32-bit. But I put an asterisk there, meaning that as you can see, there's what's called effective number of bits, ENUB. And so if you're looking into data sheets of ADCs, there's what this data sheet states it can do, but then there's effective number of bits. And this is where you go into the depths of the data sheet and the converter itself. And there's many different settings that have to be met and criteria that have to be met in order to extract the maximum amount of bits from that converter possible. So in order to get those full, say you wanted to get 32 bits out of it, there's a lot of different nuances within the datasheet that have to be met, whether there's a gain stage set up correctly, there's speeds, like different frequencies of operation. In order to get those bits, it's usually not at a high speed. It's almost always at a slow speed. So the slower the sampling rate, the less noise internally to the chip, the more it's able to average. Also, there's a lot of averaging and functions applied and different filters that are applied on these chips. So to really get the full precision of bits, it's a little bit of a trick because it may say on the data sheet that you can reach this number, but in order to achieve it, there's much more to it than just stating that it's going to achieve that. So I've seen a lot of competitors and I've seen a lot of instruments state metrics and they use an ideal metric that's stated by a data sheet. But in order to really achieve the full metric of bits, you have to go through the very deep stage of analysis on your analog to digital converter to get those maximum bits. And there's got to be supporting circuitry around it to achieve it. So just because it states a number doesn't mean that the instrument will actually achieve that. And that's part of the challenge with designing a high precision measurement instrument. The last one I want to talk about is the integrating ADC. And this one was a fundamental design that has been around for a long time, but a lot of the high precision metrology DC measurement and multimeters use this type of architecture. It's a great architecture for slow speed DC applications in a lot of metrology level labs. This is what you use to measure, extreme voltage precision. The challenge with it is in order to get that kind of precision out of an instrument, it's very slow. It has to be averaged over a lot of power line cycles. So a lot of these instruments, they have 600 to 1,000 power line cycles before it takes its initial measurement. So it can be minutes between readings. So for our kind of application, there's a balance of sweet spot between, sampling speed of your ADC and precision. So there's always a trade-off with these things. So we use a lot of equipment that have this integrating ADC in it to benchmark our equipment, but we wanted a little bit more sampling speed with our equipment. So we use the Sigma Delta. It's also very expensive to build and design an integrating ADC circuit. There's a lot of challenges that come with designing one of those types of circuits to support it. So it's an area that is not very friendly to the designer or equipment to build for their system. Next slide, Stephen. So to go more into detail about ADCs, you have to understand there's a measurement sweet spot in ADCs. There's what's known as the linear region. And if you look at this chart over here, you can see what's called the measurement sweet spot. And this is the region where an ADC itself has its optimal signal conversion. So basically the maximum signal with the minimum amount of noise. So an ADC, typically they have a range of 0 to 5 volts. And as you approach the 0 volt, you approach what's known as the noise floor, and that's where your signal noise, as Stephen's highlighting there on the left, starts to become evident. As the signal itself gets lower and lower, the more noise is introduced. The opposite is true as you approach the top end of the ADC window, you hit what's called saturation. So there's a cutoff circuit inside an ADC where it starts to saturate once it goes beyond its voltage level of capability. So why this is important is you need to be able to run in the measurement sweet spot at all times in order to get guaranteed data conversion the way we want it to. And so if we look over on the side, you can see there's a formula I want to go through. Basically, it explains that when there's a 24-bit ADC, in this example, it's using a 12-bit ADC. So the voltage window is 0 to 5 volts. 12 bits is the resolution of the ADC. So that means that there's 4,096 steps, 2 to the power 12. So if we were to convert that to a measurement resolution, as we were discussing earlier in this presentation, it drops to a 1.22 millivolt resolution. That means that the minimum step detectable change that the ADC can handle is 1.22 millivolts. So a 12-bit ADC would only have a 1.22 millivolts sensitivity. That would be the minimum step size that it could detect and change. Now, when you start to get to the higher precision side of things, when we change that number to a 24-bit, and if we've maximized the circuit around it to be able to capture the full range of an ADC, you can see that that resolution sensitivity jumps down to 298 nanovolts from an ideal standpoint. So if we were able to get the full maximum signal through the 24-bit ADC, if we follow the datasheet correctly and we built the circuit correctly, we should be able to detect a sensitivity of 298 nanovolts. Now, this is obviously an ideal calculation in an ideal world. So, but that would be the sensitivity that the analog to digital converter could convert. So in that measurement sweet spot, we'd be able to detect changes of that level. Next slide, Stephen. All right, so that's great. And so we have a little bit of a diagram here that I want to go over. And basically, if we look at it, we have ADCs obviously for current and we have ADCs for voltage. Now, since we're measuring a cell, the cell voltage that we measure is usually between 0 to 5 volts. So from a measurement standpoint, that's great for an ADC because it always falls within the sweet spot. So building the front-end architecture is quite friendly to measuring a cell just based on the voltage that a cell operates in. So it's a more straightforward part of the design. But when it comes to the current, when we actually want to measure the current through the cell, we have to do what's called ranging. And ranging is when you basically are setting up a switching network to measure a shunt resistor in line with the cell. And inside that is what the current source circuitry is pushing and pulling from. And it's detecting how much current is flowing in and out of the cell. Now, we have to have ranges because if we don't have ranges, there's the measurement window won't be able to be operated in. So as you can see on the left-hand side here, we have ranges to be able to source and send different levels of current, because if we made one range for it all, we wouldn't have enough sensitivity at the different current levels. So if we just had one resistor that was spanning across the whole range, as we got lower, we wouldn't have the sensitivity at the microamp level range that we need, because the voltage signal at the ADC level would start to hit that signal noise ratio. So that wouldn't work as from a measurement standpoint. It will still operate within that window, but your resolution is going to be less and less detectable. So we create ranges so that we're able to keep on zooming into the measurement sweet zone for a wide range of current ranges. So that's how, in theory, how you switch between. Now that stay on that one, I want to cover a couple of other things. The challenge with that comes with that is, also we have to make the resistor values optimized, because as you increase current, as Stephen was saying earlier, you have to worry about I squared R, and the power that you're measuring and dissipating across those ranges starts to become a problem. So managing heat dissipation across those sensing resistors becomes a challenge. So you have to have different ranges to also manage the heat, because if you don't manage the heat, then the drift will come into play, and your measurement for your current will all of a sudden be biased and offset and incorrect. So the ranges don't just play a fact in the ADC measurement, but it also plays a fact in the reality of the physics. Maintaining a stable and accurate measurement, we have to switch out depending on the amount of current that we're applying to manage the heat. Okay, we can jump to the next slide. Another part that I'd like to discuss is, and it's not an insignificant part, is the grounding in a circuit. It's not something that it's usually overlooked, but from a designer's perspective, circuit grounding and PCB layout is a major part of how a system is going to be successful. The grounding path, making sure that we route the return currents from the circuits in the proper way, away from sensitive analog circuitry, but keeping into account, where the digital noisy circuitry are. In these high precision applications, analog circuits are very, very susceptible to noise. And so your grounding paths and the way you ground and lay out your circuit plays a major part in how well the precision comes through and the accuracy comes through. So a few of the things that, we look into when we're designing these multi-layer boards is grounding impedance, how wide the traces are to manage the power. So specific copper planes need to be laid out in specific ways to route the currents in ways around the sensitive circuitry and to avoid noise sources as much as possible. We try to use what's called a star point topology. This forces return paths for the currents to go to a single point, so that when you're voltage referencing your ADCs, they're as accurate and as tight as possible, because if they were going to different places on the PCB or different places within the instrument, you have voltage differences, and that's going to throw off your measurement readings that you're going to see on the software screen eventually as it's processed. Analog to digital and digital circuits must be separated. If they aren't separated, what you end up running into is the noise sources from digital crystals that are resonating at high frequencies will start to be picked up on your sensitive analog noise as your sensitive analog front-end circuitry. So it's always a balancing act where to place these items. Even though on a schematic, it's easy to see from a theory standpoint how it should be laid out, putting it onto a PCB itself and placing it is a lot more challenging. Reducing the distance between critical circuits as much as possible, especially in the analog, is always something you have to look into. And then shielding and guard rings around components that need protection more than others. This is a way of cutting out PCBs and making sure that we guard and ground things in a way that is friendly for the analog circuitry, and balancing that with the digital circuitry. And so since we're talking about digital, I also want to just touch briefly on the importance of getting that analog digital measurement through the pipeline. So now we've converted that analog signal from the cell, whether it's a voltage, a current, temperature, we now have converted it to a bit stream. That bit stream has to get through the boards to the PC through the software. So I've wrote a diagram here. So it's converted at the ADC level. Then there's application-specific processor that handles the first stage on the channel board level and moves the data from that to the main system processor. The processor then has an operating system on it and different controls, and that's sent through a packet through Ethernet. And then the packet is then sorted and parsed into the application that you see on the PC. And that's where, there's the database and the data entry is collected and then processed for the customers to view. And so we can't negate the digital side, because if we can't process the digital bit stream through accurately, then we can't collect the data the way we want, and the measurement precision and accuracy was all for null. So it's all tied together, and it all is important. Every stage and every layer ends up contributing to whether the data that we see as the UHPC high precision level is good or not, all plays a part throughout the whole signal path. Next slide, Stephen. So now we're going to talk a little bit about some testing that we've done by third party as well as internally. So in the past, we've sent our instruments, in this particular case, it's our 2 amp module, to a third party to be benchmarked. It's a calibration house that we work with that's ISO accredited, and we wanted to make sure that we were impartial with our testing, and we were doing methods that followed through by other organizations, and that the testing that we were doing could be replicated and repeated in a separate institution, the reproducibility aspect of the product, and make sure that we were meeting the compliances the way we expected and our specifications were true to what we wanted. So as you can see over here, highlighted in the green, you can see the ppm metrics. We have it stated at 100 ppm is what we wanted for a tolerance level. And then through the tests, through the multimeter readings, they used a benchmarking 8.5 digit standard meter with precision reference stunts that are traceable, and they were able to basically repeat the measurements that we were able to capture here in our labs, which gave us the confidence to, publish the metrics the way we publish, because we are able to get a third party that is audited and accredited to replicate the data, which is very important to make sure that you're verifying and following the data correctly. And so we want to ensure that the integrity of the data is as high as possible. So this is the critical part of third-party benchmarking. So we also then conducted an internal study with competitor equipment and source meters, and we wanted to use, and we followed a similar process using reference standards that we have that are traceable, and our own reference meters that are high precision and traceable to national standards. And we wanted to run comparison tests on specifically voltage and current and see how we stood up against our competition and from a performance standpoint. Next slide. So basically what it came down to is we determined that the UHPC has 10 times the accuracy, 5 times the precision in our current measurement than the next leading cycler. And to achieve and verify that, we've used traceable resistor standards to the highest precision, as well as a high precision metrology meter on the market that's been the DC voltage standard for 30 plus years, and with the highest specifications possible purchased to be able to perform at that level. And so as you can see here, this is a chart that's outlining the different current ranges that we were benchmarking and how we stacked up on precision as well in the full scale range and accuracy in the full scale range. So we specify specifically with our measurements, we try to follow the ISO guidelines and do a 4-to-1 ratio with our measurements to make sure that when we're doing our expanded uncertainty and our measurement uncertainty, that it falls within a 4-to-1 ratio of what you're measuring. So that's why when we specify, you can see that our specifications, all of our measurements fall under the certain accuracy specification. Whereas if we look at our competition, you can see their specified accuracy doesn't quite fall under the same line. So basically we can tell that there's a little bit of too tight of tolerance that's been set for their specifications. And as you can see, the reference source meter, they have a specification set where their measurement accuracy is quite conservative, and we can tell that everything falls within that. And they're a little bit higher, but it's a very good instrument, but it's more of a general purpose instrument, whereas the NOVONIX instruments and the competitor were more specified and designed towards cell specific testing. So we have advantages where we were able to tune the instruments to be tight in the specific application that we're running in. I'm going to hand it over to Stephen to add a little bit more to that slide. I know he wanted to talk a little bit about it as well.
Thanks, Mike. Yeah, so this slide here goes to ask kind of the obvious question when looking at those comparisons is, what does this really mean? These specs look pretty good. So what's the difference when looking at those two? Basically an order of magnitude difference in accuracy and precision between the competitive equipment and our equipment. And so even just kind of almost reverse engineering what the performance should look like from the inaccuracies stated here, we can guess what the performance is going to look like. So this direction in charging was actually overcounting in current, which we were able to benchmark. The discharge was undercounting, For simplicity, we showed this all as the absolute values, but it was actually undercounting the discharge current. And when we go through and just kind of back of the envelope calculate what we should see in psychometrics, we would expect to see about 10 milliamp hours of excess or mismatch in the charge and discharge capacities, which lead to this kind of offset in a metric called charge endpoint capacity slippage, which when we actually tested identical cells on the two systems, we saw almost exactly that difference. And then we expect to see a discrepancy of about 0.003 in coulombic efficiency just from this mismatch, which also translated almost perfectly to the performance that we measured in the cells, along with a little bit of issues with precision and repeatability of the measurement. But this just goes to show that these measurements do really matter, especially when trying to look at cell-to-cell variation or differences in electrochemistry. So just wanted to bring it back to cell testing for just a minute, and I'll pass it back to Mike to wrap up the hardware design discussion.
Thank you, Stephen. So in short of it, where we see where our competition's falling short is we take great care into looking after the signal path and all the layers that follow through that. There's a lot of time and energy spent over the years understanding and maximizing every little piece of the signal path and making sure that we've done everything possible to maximize that signal gain from the cell as non-intrusive as possible, but as accurate as possible. We feel we have superior schematic and PCB layout in our systems. We've taken a lot of care into component selections, and another area that I'm going to touch on soon will be calibration. We've spent a lot of time mastering that part and tuning our processes to make sure that we've optimized every aspect of that. Environmental considerations, we have state-of-the-art environmental labs here where we're able to control all those factors in the environment and control the metrics and the instruments in the most ideal conditions as possible. And we feel we have the optimal support and the industry knowledge to back everything that we're talking about today. Next slide. So I want to touch a little bit on calibration and how it plays into repeatability and reproducibility. So repeatability is the ability to repeat a measurement, and then reproducibility is taking that instrument and unbiased setting it up in another location and being able to repeat the same outputs that we were able to produce in our labs. So calibration, we spend a lot of time with many different meters and high precision tools to verify our methods and make sure that we follow tight industry compliances and make sure that we have lab processes in place and methods to minimize the amount of drift that the systems are going to have over time and maximize the quality of signal that the instrument has before it ever gets to the customer site. And this helps customers at the end of the day because it makes them able to trust the instrument more than the competitors, and it makes it a very, very good instrument to run for a lot of years. So calibration is a very important process because we've seen from competition methods that use functions within multimeters where if you use like the current shunt internal to the multimeter, if you check the specification sheet of those devices, it doesn't exactly match a high precision output. There's actually quite a bit of error. It can lead to thousands of BPM error depending on how you set up your calibration and how you run it. So we've spent a lot of time designing methods and with specific custom equipment that's been purchased in our labs to be able to replicate and produce the highest form of accuracy measurements that is traceable back to lab standards. And so next slide, Stephen. So I just want to kind of wrap this hardware section up with the main key takeaways. Basically, hardware design directly impacts the measurement quality. It can't be understated. Every component and element that interacts with the signal path when it comes to the UHPC, it's important to maximize the data integrity and the signal and the quality of the data you're getting from your instrument. Understanding ADC ranging and the ADC conversion and signal optimization is critical when it comes to making a great cycler or even any high precision instrument. The grounding and PCB layout are major factors in determining whether accuracy of the readings in the instrument are good or bad. And there's usually many iterations in a design that it takes to get the grounding and the layouts perfect for the channel boards or the circuits that you're using in a high precision equipment. Digital communication architecture can determine the scalability and the adaptability, and it's not to be minimized in its importance, because to get that clean data from the converter to the software, it's important that the design and the architecture of the digital is correct and scalable, and otherwise your data getting from the cell will not match what you expect it to match. Repeatability and reproducibility are what's most important when trusting a specification sheet. And so calibration plays a major part in that being the case. So in order to maintain those specifications, keeping a strict calibration schedule is very important to maintaining the integrity of the specifications. I'm going to hand it over to Stephen.
Yeah, thanks, Mike.
Thank you.
So just to wrap things up in just about 5 minutes or so, I'm going to go through a couple applications of what we can really do with all this, why it really matters, how it can be valuable, and then we'll get into about 5 minutes of questions. So I'm going to run through these really quick. So this is all of these use cases you can find on some of our other webinars as well, if you want to dive a little deeper. So this is an application that's very close to our hearts at NOVONIX in terms of cathode development. So here's an experiment in which we were testing 2 different cathode materials and making full cells out of these in our pilot line, pairing them with the same anodes, the same electrolytes, and putting these cells on typical cycling on a low resolution tester for many, many months, and kind of without warning, seeing one of these materials fail. There was no change in impedance, no change in capacity loss, and around 2,000 cycles, one cell just failed. And it's really hard to find, any information in low resolution data that might lead to this conclusion early. So we use UHPC on any of our or all of our materials development. After formation, we put some cells onto long-term cycling and other cells onto UHPC cycling. And just in really days instead of months of cycling, we can look at metrics like coulombic efficiency. You can see here this really zoomed in axis with triplicate cells. So these measurements we have very high confidence in. There's very good accuracy and resolution required and precision required to make these measurements. And we can see just within days of this cycling that there's a difference in coulombic efficiency. And this is driven not by differences in capacity fade from either of these materials, but from this metric that we call charge endpoint capacity slippage, this proxy to measure things like electron donating reactions, like electrolyte oxidation, transition metal dissolution. And just within a couple days, we can see that this rate of these mechanisms happening in this green material is twice as high as the rate happening in the black material. And these processes that lead to this cell death are present day 1 of cycling. It's inherent to the electrochemistry. And so if you can count electrons accurately and precisely enough, you can get this information really quickly, go back to the drawing board or make informed decisions that do really high throughput experiments rather than waiting months and months. Another fairly obvious use case of this is quality control. Right now, especially in gigafactories, you're producing millions of cells a day. These cells in the EV world need to go through pretty robust QC processes, sometimes taking weeks of storage in order to sort cells and look for differences in voltage drop. And so what we can do with UHPC is hopefully speed this up and do intra or inter-batch comparisons of cells as they come off the line to detect really small differences in these self-discharge mechanisms. So this case study that we did was using 4 different vendors of cells from tier 1 to tier 3 vendors with different cell designs, just to look at what kind of differences in quality we could see by measuring self-discharge current during a voltage hold on all of these cells. So we did this on 50 cells of each of these vendors. And what the next slide will show is after this constant voltage hold, measuring down into the microamp range, is the distribution in a histogram of the self-discharge currents. at the end of this testing. So the key takeaway here that I want to draw everyone's eyes to is the tier 1 cell has a really nice, tight, and symmetric distribution, where the width of this, the relative width compared to the signal, is about 2%, whereas the tier 3 vendor has kind of a broad and non-symmetric distribution, more outliers or more counts of cells sitting at a higher rate of self-discharge. And keep in mind, all these cells have already gone through the standard QC process. And the breadth of this distribution being about 9%, so almost 5 times broader than the tier 1 distribution. And even in cells like LFP, where QC measurements can be a lot harder because it's hard to differentiate between self-discharge and IR drop when measuring voltage changes. We can get like sub-ppm cell-to-cell differences, with ppm being described as ppm of the full capacity or C rate of the cell. So this can be really valuable for manufacturers or for downstream people that are receiving cells and putting into end uses, or even second life sorting and understanding of quality in cells. Another application is, of course, lifetime prediction. If we can measure these rates of mechanisms that are happening in cells really quickly, can we use this to kind of give another layer of value into machine learning models, add features that are driven by UHPC measurements? So we did a case study on this with a company called Sandbox AQ, leveraging their knowledge of machine learning and testing cells on both UHPC and also just standard lab cyclers for a long time, pairing that data with short-term UHPC measurements. And so what this really was able to let us do is, under very different conditions, temperatures, voltage ranges, trying to turn on and off anode versus cathode degradation, make a really hard model to generalize. We were able to really improve classic model features that are just gained from looking at early cycling. Once we layered into that the UHPC data, which gave really detailed information on the degradation mechanisms happening, the rate of these mechanisms that really lead to these early rollovers and failures of cells. So we were really able to improve how machine learning models of lifetime can predict. This can be really useful for warranty prediction or even just interpreting how long a new chemistry might last rather than testing for months or years. So I just want to touch on here as a conclusion that existing cell testing equipment that covers all of that other range of that triangle really excels at a ton of things that are really needed in battery research and development. And all of this really has a common theme where these excel, where small uncertainty in raw data or metrics don't really matter. Testing cells to end of life, etc. And the gaps that we try to fill are where even small uncertainties matter a lot. Material technology development, doing things really rapidly, early QA detection. So we're really trying to address these gaps, and it's really a valuable asset combined with any other equipment in every lab. So thank you, and we'll probably have time for just 1 or 2 questions.
Yes, a couple. Thank you, Stephen and Mike. Now we'll move into the Q&A portion of today's session. And thank you if you have already submitted questions in our Q&A box at the bottom of your screen. Please continue to do so. And we will do our best to get to all of our questions. So the first question I have here is, how high of amperage can UHPC go to? And do you have plans of going higher?
Yeah, that's a good question. So UHPC currently we go up to 20 amps, and for many of the reasons we got into during the webinar, it's very difficult to push higher than that. We always have plans of going higher and higher, so we'd like to see someday how high we can go. But that's really why there is that kind of cap to what we're capable of, is a lot of the issues that we were addressing in the talk.
Great. And can UHPC be done for pack testing?
Yeah, that's also a question we get a lot. For pack testing, because you're dealing with so many other components, you're not just dealing with one cell, making really tight measurements of capacity or coulombic efficiency, even on many cells, you start to have issues introduced into that kind of signal path. Even thinking about what Mike was discussing with all these different connections and voltage differences and changes and drops across something where kind of the benefits of doing UHPC testing don't are a lot harder to do, I guess, when you're doing pack testing or many cells in parallel or series. So there may be it may be more applicable for doing cell development and chemistry development at the cell level.
Great. Do you lose the benefits of conventional UHPC by testing at high rates in more complicated drive profiles?
Yeah, and for some of the same reasons we had mentioned, kind of like with pack testing, there are other nuances to the testing where you may have high rates introduce self-heating. They introduce other types of kinetic failures. It also decreases the amount of time you spend during that cycle, which also means that things like electrochemical degradation mechanisms, there will be fewer of them that happen in a cycle. So a lot of there are still benefits to doing some types of high rate testing with UHPC. It really depends on how you're going to analyze the data and what you're going to do with that data.
Can you explain how to use your equipment to measure self-discharge, which you briefly touched on in your slides?
Yeah, in those measurements, we were using a constant voltage hold, so applying, charging the cell to say top of charge, 4.2 volts or 3.65 volts in an LFP cell, and just holding the voltage stable there. You could really do this at any voltage. We just chose top of charge, and eventually, when all the kinetics kind of die out, the cell is fully charged. The self-discharge current, or the current that you measure, the only thing that can really be due to is some of those extra electron processes, like an electron bridge within your cell that could be a soft short, or redox shuttles shuttling electrons across the cell and then through the external circuit would be what you're counting then as your self-discharge current.
Okay, great. And we will take one last question. How long did that measurement take?
Yeah, that measurement can really be as long as needed. We've done some of those measurements just over a few hours. The measurements I was showing were 72 hours, so about 3 days. But as you walk backwards, you can kind of optimize the amount of time spent based on the signal that any given cell model might kind of give you, or the kinetics of that cell model. You can kind of optimize that time and shorten it as much as possible, depending on what really the end goal is.
Great. Well, I think we have to leave it there. A big thank you to Stephen and Mike, and thank you to everyone who joined us today and shared questions during the Q&A. We hope you found this session both informative and valuable. As a reminder, we will be sharing a link to the recording tomorrow to all registered webinar participants. If you'd like to explore UHPC further, we invite you to watch our YouTube playlist on UHPC, where you can access all of our previous UHPC webinars. And to stay up to date on future webinars, company news, and services, you can also follow us on LinkedIn. On behalf of the entire NOVONIX team, thank you again for spending your time with us today. If you're interested in discussing how our UHPC technology can support your programs or projects, please reach out through our website at novonixgroup.com.